All right, how's it going, geologists? Hope everyone's doing well. So you made it to lab 3, and I have noticed a few people haven't been handing in the labs. Um, so if there's any issues with it, if you have any questions or technical kind of difficulties, I know the online format can be a little weird to navigate. But if there's any confusion, please reach out to me. Like, I'm here to help you. I want to help you. So please don't hesitate to ask if you need anything. But let me explain lab 3. So lab 3 is going to be looking at earthquake magnitude. So with earthquake magnitude, we measure it on what's called the Richter magnitude scale, which is a logarithmic scale. So it's not linear, which means after each point, it's going to grow a ton. And this picture does a really good job of showing it. A 1 versus 2 versus 3. It's going to grow exponentially there. And two common ways to measure kind of earthquake power would be amplitude and energy. So amplitude, for every whole number, the amplitude will increase by 10. So that means a magnitude 2 is 10 times stronger than a magnitude 1. And a magnitude 5 would be 100,000 times stronger than a magnitude 1. So it grows really, really quickly. And then for energy, energy increases by roughly a factor of 30. So a magnitude 2 is 30 times stronger than a 1, and a magnitude 5 is 24,300,000 times stronger than a magnitude 1. So earthquakes are very, very powerful. It's pretty cool stuff. So magnitude versus intensity is something that's thrown around a lot. Magnitude is measured by instruments, and it is the same regardless of conditions. So like a magnitude 4 in California is going to be measured the same as a magnitude 4 in Alaska. But intensity is more dependent on different conditions and how people felt it. So some conditions could include distance from the epicenter, and we were looking at that a little bit last week. But one thing to touch on would be if you're right on the epicenter, it's going to be really strong, versus if you're really far away from the epicenter, those waves are going to dissipate and get weaker the farther away you get from the epicenter, and it won't be as intense. Ground type would play a big role. If an earthquake occurs on really loose soils, that's going to feel a lot more intense versus an earthquake that occurs on really hard rock. And things like infrastructure and buildings would play a big role. If you're in a house that's meant to take earthquakes, that's going to feel really different than a house that isn't really meant to take it. And then number of people is also a factor for intensity. If an earthquake occurs where nobody's around, it typically won't be called as intense just because there wasn't people there to give data, versus if it happens in a really densely populated area. And table 2 here gives a simple just kind of summary of magnitude and intensity, roughly, even though intensity can vary a little bit, and common descriptions for what that would feel like. Okay, with that, I'll jump in how to do the lab. So this is a nonogram, which is a great way to determine magnitude if you have distance and amplitude. So this little image in the corner here, given in the lab, shows the arrival of a P and S wave. Remember from last week, we can find the SP difference. And on this example, that's giving it as 24 seconds. And then the amplitude is halfway from that wave up. And it's measured in millimeters for this nonogram. So using nonograms is really simple. In the lab for using it, it's already going to give you the SP difference and the amplitude, so it's not too bad. You would just plot a point for the SP difference, so this is 24 seconds. We'll be plotting up at 24, and the amplitude for this example is 23 millimeters. You would draw a line in between, and where they intersect is the magnitude. So For this, you don't have to actually draw them. I find it easy to just hold like a ruler or a piece of paper, a flat surface, just to see where they intersect. But feel free to do this and draw it if that helps you. It's entirely up to you. So using seismograms and travel time curves. So we did this last week. You should all be experts on it. The lab will be asking for the SP difference. That's going to be that time difference between when the P wave and the S wave arrived. So we can just mark where that start is and come down, and this axis is in seconds. So that looks like 3 seconds. And then the S wave here, that's 6, almost 7 seconds. And whatever that difference is, that would be your S minus P difference. I think the lab calls it an SP lag time. Same thing. And then when you have that seconds, you can come over to your time travel curve. I did an example of 16 seconds just to show that 16 seconds is inferring to the gap. So here to here is 16 points on that graph. So once you find that gap, where that falls is that distance. So on this example, for a 16-second SP difference, that would be an epicenter distance of 140 kilometers. So this is all stuff we did last week. Cool. So then question 6 is asking you to find the amplitude and ground motion. So to find amplitude, it's not too difficult, I'd say. There's 2 easy ways to do it. So the lab suggests measuring the full wave and then dividing by 2. You could also just measure half. And when you're measuring the biggest wave, I should have mentioned first. So it doesn't really matter if it's the P or the S wave, whichever one is bigger is the one you're measuring. So for this first one, I would measure the P wave, the second one, probably the S wave, and then the third one, definitely the S wave. And so after you measure it, make sure to measure in centimeters. We have to convert to micrometers, which you can do by multiplying by 10,000. And then after that, we can find the ground motion by multiplying that amplitude in micrometers by the given magnification. Let me show you what I mean. My share screen bar is blocking me, but here we go. So we're filling out this table. Once you have the amplitude in micrometers, just multiply by the magnification, and that will give you ground motion A. And then the next part is going to be trying to calculate the local magnitude using this equation. And it looks spooky, but it's not actually that bad. A is that ground motion you just calculated, and D is that epicentral distance you just calculated from the time travel curve. So you use those 2 and plug and chug, it'll spit out a number. So, and it gives a nice little example of just the math and the breakdown. Yep, so A is ground motion and D is distance, and that will give you the local magnitude. Okay. So question 8 is asking for intensity. You'll have a few blank tables that look like this, which gives different cities and then descriptions of what the people there felt. And you can assign a number to each city based off of the given chart. And then once you have each of the cities assigned an intensity number, we can plot them on an isoseismal map. So it'll look something like this. You'll want to put the numbers over each city, and then kind of like connecting the dots, kind of just circling each group. So we're grouping them by like 1 to 3, 4 to 5, so on. Yep, it's not too bad. and then you're going to want to upload a picture of this when you have it filled out. So you can either use a computer program for it, whichever computer program you're comfortable with. You can also print it, hand draw it, and take a picture and upload that, whatever works for you, whatever's easiest. And yeah, that's all I have for you. So if you have any questions, please let me know.